Okay, the second and final topic of this lecture is to discuss about design, construction, and operational constraints, but also recent developments. Again, this topic is treated deeply in chapters 4, 5, and 6 of this open access book. In chapter 4, about design, 5, construction, and 6, regarding operation of anaerobic reactors. I'm going to talk about some specific points that many times do not appear or are not well discussed in the real world. So the first one that I'd like to call attention is scum accumulation and lack of inadequate scum removal devices in USB reactors. So the scum that accumulates, especially inside, scum can accumulate inside the three-phase separator, the GLS separators, but also on the surface of the settler compartment, if the settler compartment has baffles. If the settler compartment has no baffles, the scum is formed in slow rates and will not pose problems in the following post-treatment unit. But I'm going to talk specifically here on the scum that accumulates inside, in the upper part of the three-phase separators, in the interface with the gas chamber, because this constitutes maybe the main operational limitation and problem in most full-scale plants in Brazil. At least this is our experience. Here you can see the aspect of the scum layer that is formed inside the three-phase separator. This is one general view. This is the aperture of the three-phase separator of the gas chamber. And here is the aspect, how the scum looks like if it stayed without being removed for long periods. And it becomes a very thick and concentrated material, very, very difficult to remove. For instance, it's not possible to pump, to suck it. It's necessary first to disaggregate, to break this scum to allow its removal, and from very small apertures. So this is an important point. And because, and why this is important? It shows us that this sort of mechanism to remove using sucking pipes or using pumps is not the ideal one, because you open these, you have gas release, you have other problems, you have security problems. This is not efficient. There are many, many problems with this solution for removing scum. Here is another view of one scum that was removed via one device that I'm going to show you in the next slides. Here is another detail of that about those two slides, the characteristics of the scum accumulated inside the three-phase separator. So this type of scum, solid and concentrated and thick, can hamper biogas release, so it blocks the biogas liberation, and the biogas will go to the apertures to the settler compartment, taking gas bubbles inside the settler compartment. Of course, you will disturb solid sedimentation. It can damage, in some case, the GLS separator, especially if it's made on fiberglass. This material cannot be resistant enough to the pressures, the loads that are applied by the scum in the walls of the three-phase separator. And as I said earlier, it constitutes nowadays in Brazil perhaps the main operational problem in most full-scale plants. And what we propose? We propose this sort of removal device that we call the hydrostatic scum removal device. It's based on operations that we need to keep some pressure inside the gas chamber and to install one channel, a small channel inside the gas chamber in a level below the water level in the settler compartment. So it works in 4 steps. We keep this gas chamber pressurized, so the scum layer will be here, close to the top of the collection channel. Then we release one valve outside the reactor, so there will be a pressure relief here, so the scum layer will go up and go inside the gas chamber, inside the channel. Then after the scum is removed, it's clear now, we close this valve and the pressure is established here. How is this in practice? Here we have one figure that is in the book, figure 6.14, where you can see that this gas chamber here communicated with one hydraulic seal where we can control via the water level, we can control the pressure here. So if you put 5 to 10 centimeters pressure here, this 5 to 10 centimeters will be transferred to here, and you put another 2 to 3 centimeters below the top of the collection channel. And with this, we can operate in this way that I showed here. Open this valve that is outside. And here is in practice one 3-phase separator. Here in the upper part is the scum channel, and this scum channel communicates with the exterior of the reactor with these pipes and valves, and open this valve, we can remove the excess scum that accumulates. And here we have also one recent development, what we call a modular 3-phase separator that's made in fiberglass. And this 3-phase separator comes with inspection apertures that allows, when necessary, to see the scum and the remove of the scum via this internal channel. And it has also the collection weirs together with the 3-phase separator. So it's a recent development, and more details are in the book, in chapter 4 of the book, about this sort of device and how to design and specify these devices to remove scum without having to open these apertures. Is removed hydraulically, only operating these external valves. Okay. Another construction problem maybe some problems are combined. There are problems related to design, to construction, and to operation. But we can say now, today, that most of the operational problems are related to some sort of design or construction. So it's difficult to analyze one problem specifically to design or construction and operation. Usually they are related. For instance, here, inadequate design of the preliminary treatment units. If the design is not okay, there will be a great entrance of solids, especially debris, rubbish, that is present in the wastewater, especially in developing countries, but also sand, and this can pose serious problems to the reactor itself, but also to the characteristics of the sludge and scum, and also formation of dead zones. Here we can see the aspect of the material that enters or incomes to the wastewater treatment plant. Here is one chamber located just before the preliminary treatment units. A lot of material, including rats and other animals, big materials. Here we can see one sieve, 6 millimeter sieve, that is installed after one fine screen. It means that if this sieve was not present here, all this material that you can see here retained in the sieve would have entered the anaerobic reactor. So, and we know that many sewage treatment plants, they only have coarse, maybe fine screens, but not sieves. So sieves becomes one important structure to be planned, designed to avoid this material going into the reactor. And here we can see a lot of sand that is accumulated inside one feeding box on top of one USB reactor. And why this sand here? It's here because it was not removed in the preliminary treatment unit. And why is that? Possibly because the surface loads designed for the grid chambers were higher than the specified, the adequate ones, so the sand did not sediment, did not settle in the grid chamber. So those are problems related to the preliminary treatment system. And we can say here that none of them are related to operation. They are related to design and maybe to construction. Another problem that we have been detecting in practice is the installation of the collection weir. Here we can see the collection here with that has no baffle, but we can see that a lot of scum is accumulated here. And why is that? Because the weir was not installed in the right position, in a leveled position. If you have an unleveled collection weir, we are going to have flow in one part of the collection channel and accumulation in other parts. So this can lead to problems of preferential fluxes and also scum accumulation, as we can see in this photo. And this is not a design and it's not an operational problem. This is one construction problem. It means that the collection weir was installed, but the level was not verified during the construction. So pay attention to verifying the levels of the collection weirs and channels installed in the reactors. And you can imagine, for instance, that if you have one reactor with 5 three-phase separators and one collection weir in each side, so 5 three-phase separators times 2 collection weirs per three-phase separator, we're going to have 10 collection weirs. So the level should be the same in the collection weir itself, but also should be the same among all 10 collection channels and weirs. So it's a very important point to pay attention during the construction. Use of inadequate materials and coatings that can cause corrosion problems in concrete and metal structures. Here you can see corrosion problems in one concrete slab. This photo was taken from bottom to top of the reactor, and in some points you can see the exposure of the steel bars. So severe concrete problems here in a concrete gas chamber of one three-phase separator, also severe corrosion problems. And here, one solution, what can be done? This is one gas chamber in concrete, but the good or the proper adequate coating was used here to protect this concrete structure. And this coating was made 20 years ago. I have entered this reactor recently, and I can say that the protection is still there. It's working properly. So there are solutions. And the point is, there is no surprise. Everyone that deals with anaerobic treatment with the design, for instance, of one USB reactor knows that sulfide will be produced, that the environment will be proper for corrosion formation. So the design should know that it's impossible to use metals and concrete without proper coatings resistant against corrosion. Flow variations, this is common in every sewage treatment plant of dealing with domestic or sanitary wastewater, sewage, because we have variations along the day, we have variations along the year, but we have also huge variations, especially in the rainy seasons. Although the systems in Brazil are designed as separated systems, one for drainage and another one for sewage, of course, there will be always connections, cross connections between those two systems. In this graph, you can see here that in 2008, we have a lower a lower flow during the winter season, because the water consumption is lower in the winter season. And here you can have the summer season, water consumption is higher. So this variation is as expected and considered in the design. Know the variations along the year, lower flows in the winter, higher flows in the summer, the same in the following year, winter, summer, winter, summer. But what is not expected in the process or the treatment process cannot deal with is that if the average flow is 60, the maximum flow rate in the rainy season should be around here, 80, maybe 90 liters per second. But we can see that in many days, the flow rate is much higher, and this is due to rainwater entering the collection system. So we have a lot of big flow rates due to rain here again in this year, again here. So rainy seasons can increase significantly the flow, and the design should take care of this. It means that the preliminary treatment unit before the anaerobic reactor should have one overflow structure to avoid that this extra flow goes to the treatment plant itself. Use of inadequate sludge dewatering systems. This is also recurrent in Brazil. And if the sludge dewatering system is not designed, is not implemented, is not operated properly, this can cause big impacts for this excess sludge management. We know that every biological treatment system has sludge growth. There is an ideal quantity of sludge, of biomass, that we should keep inside the reactor. If the amount is small, we will not have the capacity to treat the incoming organic load. But if you have sludge above the limit of storage of the system, we are going to lose sludge with the effluent, and this will deteriorate the quality of the final effluent. I'm going to show you some results about this. And also, the choice between mechanized or natural dewatering systems. So mechanized systems is more compact, has a much bigger process capacity, but many times they are difficult to be maintained in continuous operation. So pay attention when using mechanized systems to be sure that they will be working properly for continuously, because if the mechanized system is not working properly, it's out of operation, you cannot remove excess sludge, and this excess sludge will be removed via the effluent, deteriorating its quality. Another constraint is the use of inadequate hydraulic profiles along the plant. As we saw in previous slides, in the previous lecture, if this hydraulic profile is not appropriate, it can seriously impact the management of the dissolved gas, like hydrogen sulfide and methane, as we saw in the examples that the concentration of this gas, sulfide, around 10-15 milligrams per liter, methane around 20 milligrams per liter. So if the hydraulic profile is not appropriate, this gas can be released from the liquid phase and can cause problems in the environment. Another constraint is the lack of process control and data acquisition instruments. And we know that the lack of these basic instruments can significantly impact the process control. I'll give just one example. For instance, to remove scum using that hydrostatic scum remove device that I showed in a previous slide. For each scum channel, there is one valve outside the reactor. So this valve should be open for a certain time, for instance, 2 minutes every 3 days a week. And this process could be automated using mechanized valves. And usually the valves that are used are a manual one and not cannot be automated, of course. Sludge withdrawal. This is related with the dehydration equipment or way that we choose, natural one or mechanized one. So we know that USB reactors, they present a high capacity for biomass retention, but excess sludge should be removed on a regular basis. If the sludge is not removed, the excess sludge is not removed, it will be removed in any way. For instance, washing out solids with the final effluent. So the reactor, they have a high capacity to retain, to keep the biomass, but until its storage capacity. If the storage capacity, if the sludge amount is beyond this storage capacity, this sludge will be lost with the effluent, as I'm going to show you in the next slide. So many plants also do not have well-established sludge discharge protocols, especially in those small ones where there is a lack of operators in general. So it's important to have dedicated, appropriate dehydration equipment or solution. Can be mechanized, can be natural. Natural, I mean, for instance, sludge drying beds. Mechanized, for instance, centrifuges. Can be either solution, no problem. But the protocols to know, to define when and how much sludge should be discharged, this usually is not well established and should be. Here it's a very interesting graph. Here on the left you see days of operation. There are many days, 570 to 920, so maybe almost 400 days, more than 1 year in general. And here in this left axis we have the mass, how many kilograms or tons of total solid sludge present, represented by these vertical bars. And here at this stage it's 14,000 kilos, 12,000 kilos. And here we can see that the mass of the sludge is much lower, so the reactor was operated with excess sludge above this maximum capacity that we identified as around 8,000. 8,000 kilos was more or less the capacity, the storage capacity of the reactor. So it was operating at this time over this storage capacity. And what happened? The total suspended solids concentration indicated by these black marks here, points here, you can see that the concentrations were above 100 milligrams per liter, 20, 300, even around 400 milligrams per liter, when the expected concentration is usually below 100 milligrams per liter in well-operated reactors. And well-operated here means more or less to have a good management of the sludge. And why the reactor was operated with this excess sludge here during these various months and days? Because the dehydration equipment in this plant was a centrifuge. Actually, it was a filter press, and it was out of operation due to maintenance problems. And it was very difficult to get rid of this excess sludge, this passive of sludge that was inside the reactor. But when we managed to instruct the operators to discharge more sludge and reduce the amount of sludge, the mass of sludge inside the reactor to its limit of around 8,000 kilograms, the concentration of suspended solids in the effluent decreased sharply, staying below maybe 50 milligrams per liter. So it's a clear example of how sludge management is important. And the sludge management is totally dependent on the operators, but also on the dehydration unit. If you do not have your dehydration unit operating, you cannot discharge sludge and you are going to lose solids with the effluent. And here in this graph on the right, you can see also the gain of efficiency is another period, is not the same period here, but the same logics. The concentration of the amount of sludge inside the reactor was above the capacity of the reactor. So the COD concentration was above 200 milligrams per liter. And because the reactor was losing solids, when the reactor was operated with the right amount of sludge, the COD concentration decreased to around 100 milligrams per liter. So the reactor could, when operated properly, depicted one efficiency around 74% in terms of COD. And also in terms of total suspended solids in the effluent, it was high in this period, around 200, 250 milligrams per liter, these gray circles here. But when the amount of sludge was the adequate one, the reactor was operated with the right amount of sludge, the suspended solids concentration in the effluent stayed below 50 milligrams per liter. Again, a very high efficiency when the sludge management was appropriate. Process operation with low-skilled personnel. Sewage treatment started to become a priority in the developing world only more recently, maybe in the last 20, 30 years. So there is not yet one established culture on wastewater treatment and also on design, construction, and operation. So As a consequence, there is a general lack of qualified operators, and this seems to be one of the major problems in the sewage sector in the developing world. It's okay, it's one of the major problems, but it's not the only problem. As I said, we still have problems with bad designed and constructed plants. So the operation is one potential problem, but it's not the only one. And as a result, various plants are poorly operated, especially regarding the correct management of excess sludge and also scum in USB reactors, as I mentioned before. And what we need, there is a strong need to train operators and establish operational routines for excess sludge and scum management. And here, my final slide with a summary of the limitations and constraints. So temperature, nutrients, pathogens in the previous lecture. And in this lecture, we talked about gaseous emissions and design, construction, and operation constraints, but also developments. What are the good news regarding these limitations and constraints? So the good news is that most of them can be solved or minimized with proper design, construction, and operation of anaerobic reactors. So my final message here is that the problem cannot be dedicated to either design, either construction, or either to operation. We should take care of everything, proper design, construction, and operation. If the reactor is not properly designed or constructed, the operator can do almost nothing to operate it properly. So this is my final message, and I thank you very much for your attention.